Yeah, exactly.
All right, we'll get started here. We're going to just talk a little bit about the notation with the forward difference operator and then the symbol that we use for that. And then we're going to move on to the cubic spline interpolation. Are there questions before I start? Anybody have any compelling thing they need to ask? All right. The forward difference operator is, we use the delta, the capital delta for that. So delta of Fi is simply F at I plus 1 minus F at I. And we are in the case of even spacing. So that is Xi is X naught plus some number of little spaces moved over. This is the even spacing. It doesn't make sense to do this if you have uneven spacing. We then define the delta squared to be, and this should be fixed. This is plus I subscript. So that's delta Fi plus 1 minus delta Fi. And then we just keep going like this. And that allows us to write the first divided difference in this manner right here. Okay, and then we similarly can write the next one like this. These are sort of it is a notational convention. And in practice, what we're going to always be doing is using that table to get the coefficients of our interpolating polynomial. Okay, we've already had that from before. Now we can write this as delta F1 over H minus delta F naught over H divided by 2H, and then you'll note that that can be simplified a little bit, like 1 over 2H squared, delta squared F naught. Okay, that's this coming in right here. So, and in general, we can just continue this procedure up, and in general, we get this, that the whichever divided difference we're talking about, the kth divided difference can be written as 1 over k factorial times h to the k times K F dot. Like that. Okay, and that just allows us now to write the Newton version of the interpolating polynomial when the node spacing is equal, like this. The zeroth divided difference plus the sum from n equals 1 to n. We already showed how to get the binomial coefficients in there. And then now we can replace the rest of it by this. There. The Newton basis interpolating polynomial with equal spacing. I'm not going to ask you to write it out like this. Gentlemen, we're trying to find this thing. We'll be setting up the table, calculating all the divided differences, going through, and then knowing which ones to select. The ones that are along the top going down. That is it with the divided difference. So next page just has that typed out again. And we have just seen the forward differences, and that's all we're gonna stick to that. You can get related formula for backwards and centered differences, but we're not going to bother with that. That is in the textbook if you want to check that out. But we're going to I think it just adds confusion. It doesn't help. So what we're going to do is just stick with the forward differences. Okay, that's it. That's all. Yeah. Sure. I can scroll back up. There we go. How's that? Okay. All right. So where are we at? We first figured out what is an interpolating polynomial? A polynomial that goes through all our data points. We figured out how to find that using the monomial basis, which you can basically do by solving a system of linear equations. Then we recognize the problem with that is that the monomial basis results in sort of ill-conditioned problem of having large and opposite coefficients and cancellation error. So then we went to the Lagrange basis, a big improvement. Then we recognized that we can pre-calculate some things while using the Lagrange basis, the barycentric weights, to speed things along if we're going to be always using the same interpolating nodes. Then we realized that, hey, the Lagrange basis suffers from the problem that every time we add a new data point, we have to recalculate all the basis vectors. We don't want to do that. So now we have the Newton basis, which has the advantage that when we add a new data point, we simply can just calculate the next little thing to add and we're done. We don't have to recalculate everything we've already done. And then after that, what we've done this last little bit is just recognize that we can compact down the notation. All right, so all of these interpolations suffer from a problem, which we are now going to address. So we're going to skip Hermite interpolation completely. We're not covering that. I think I posted my stuff in Canvas. If you're interested, we're not going to bother with that. It's almost never used. So now we're going to go to the cubic spline. This actually is used a lot. This is a very standard method, and it has a lot of nice features. Okay, so we talked just briefly about how to look at the Newton stuff when the nodes are equally spaced. By nodes equally spaced, I mean you have some underlying function that you wish to interpolate, and the nodes equally spaced means looking like this. This is where you're taking your data at equally spaced intervals. Seems actually at first blush not to be a bad idea, right? So you're going to take these data points, and these things are equal. That's what it means, equally spaced nodes. So when the nodes are equally spaced, problems happen. And what does happen is, here I can illustrate this here with a graph. Here we have a function in blue. So the blue line is the function that we're trying to interpolate. That is f of x. And then we decide to take 10 values of f of x, and we want to put an interpolating polynomial through them. So that's 10 data points. That's the nodes equal to 10. That's 10. And we get this green interpolating polynomial. As you can see, it doesn't, so that the green thing there is p of x. as you can see, it doesn't match f of x everywhere. But it's, you know, particularly in the mid-range, it's not so bad, and it's a little bit bad at near the endpoints. So then you would maybe think, and it would be reasonable, in fact, I should think, that if I increase the number of interpolating points and cram the polynomial through it, I'll do better. So here's what happens when you increase the number of points up to 35. The blue and the green are nearly on top of one another all through the mid-range here. That's better. But then you get this near the end. By forcing the polynomial through all of the points, you get this oscillatory behavior at either end. And then, of course, that's the pits, because if you start to use your polynomial in these areas over here, you incur like huge errors. And nobody looking at that underlying function would think it would be a good idea to approximate the point by something way up here. Okay, this is called Runge's phenomena, and we wish to avoid it. So typically speaking, you do not want to, you have two choices really. Once you've recognized this problem, once the problem has come to light, and the fact that it's named after somebody means it wasn't totally obvious in the first place, right? Just by figured it out. We're going to see ODE solver, also the Runge-Kutta method, same guy. Okay, so you are doing this, and now you realize, okay, so I have a problem trying to get more accuracy. I have a problem when I increase the nodes and they're equally spaced. So now you have two solutions: don't increase the number of nodes, or don't space it equally. That's really that's really about it, right? To avoid this problem. So our first look at this is going to be to, instead of having our interpolating polynomial, use one interpolating polynomial. We're going to use a whole bunch of interpolating polynomials and just have each one use a small number of nodes, and then we're going to put them together. That's what we're trying to do. So the idea of our first idea is going to be to use a piecewise polynomial interpolant. Okay, so what we're going to do is we're going to take the interval, we're going to divide it into subintervals, and we're going to use low degree polynomials in each subinterval, and then just attach them all together. And get rid of the Runge's phenomena. Question about what we're doing? Yeah. So the question is, how do you choose the subintervals? And what we're going to do to choose the subintervals, we're going to imagine we've got an underlying function like this, f of x, that we're trying to get an interpolating polynomial, and we've got our data points. We've got all our data points. Now we're going to try to cram some polynomial through all of those points, but we are not going to do it with a single polynomial. And so how do we pick our subintervals? What we're going to do is pick like by data point. We're gonna look at the options here, but we could say take the first 3 data points for one polynomial, and then take like the next 3 data points, or those 3 data points for that point, and then we could do it like that. We could do a polynomial, we could do it like that. And so what we're going to ask is, you know, should we take 2, 2, 2? Should we take 3, 3, 3? Should we take 4, 4, 4? And how do we try to join when one polynomial meets the other so that it's smooth, right? So it's not done. How to choose the subintervals is done by how many data points you choose for each subinterval. Yeah, we're going to go through the options here, and we're going to see what works well. It's a really good question. That's exactly what we're going to do here. So we divide into subintervals, use a different polynomial in each one. We patch them together, and we get a piecewise, what we call a piecewise polynomial, because it's not the same polynomial across the whole thing. And it's supposed to fit fairly well, and we get rid of this Runge's phenomena. That's the goal here. Okay. First option, possible choices. We could do linear piecewise. So let's just draw what that would look like. Okay. We could just put a degree 1 polynomial, right? We could have our data here like this: x0, x1, x2, x3, x4. We have some data, looking like this. there's our data. And we say to ourselves, okay, let's just choose 2 data points for each subinterval. And then I would say, okay, that's fine then. I'm gonna take the first subinterval, I'm gonna fit like this guy through. Right? A degree 1 polynomial through 2 data points. Then I'm gonna take the next subinterval and go like that. This is what people do in grade school, right? They're like, draw a curve that goes through the points, or connect the dots, right? There. So I'm gonna have, in this case, 4 subintervals. Each one of them is gonna be interpolated by a linear a line, a degree 1 polynomial. And then if I want to understand what is the data, what is the, here at whatever, let's just call this X n or something, no, n is bad choice, X star. I'm like, hey, what is the underlying thing? Probably look at it, X star. I'm gonna go, oh, I'm in the first subinterval. I'll use the first line and I'll give you that number. That's an option, right? The dot to dot approach. It's easy to do, super easy to do. There's a MATLAB command for that, which is this guy here, where X is the nodes and Y is the data at the nodes, and X int is the interval to interpolate, is the grid to evaluate the polynomial on. So that's a possibility. It might be a valid possibility. What is lousy about this? Is it's not differentiable. Well, at all of these points, the interpolating function that you made is not differentiable at these little corners. So that is potentially undesirable. So we could have a piecewise Hermite, which we are not doing. It's because it relies on you having the derivative of the function at the data points, which you often don't have. So Hermite is gone.